Welcome to Chapter 5, Atmospheric Pressure and Wind. We are going to talk about some of the processes in the atmosphere that move the air across the world. But first we need to talk about air pressure and causes of wind. So one of the most basic examples, or probably the most common examples, of the link between air pressure and wind is inside a hurricane. Now, in the eye of a hurricane, or I should say really around the eye wall, we have extreme differences in pressure, which also, as you may know, create very, very strong winds. But inside a hurricane's eye, we can get some of the lowest atmospheric pressure readings on the surface of the Earth. So in this chapter, we're going to look at a couple of terms. We're going to get into something called an isobar, and then your three forces behind wind: pressure gradient force, Coriolis, and friction. Talk about a couple of terms when we deal with winds going around a low and a high pressure. Various kinds of high and low pressure systems. Something called the ITCZ, Intertropical Convergence Zone. And some of the other terms here that we have are linked to the global flow or the global circulation of the atmosphere. One of those things that you may have heard of before is the jet stream, and we'll get into that toward the end. So a question I have for you right now is, have you ever had your ears pop when you go up or down in an airplane or even over a hill? If that is the case, then you have experienced differences in air pressure. Your ears are trying to calibrate to different air pressure readings. So exactly what is air pressure? Well, we got to think about air as a fluid. It's full of molecules in the gas form, and they're continuously in motion. And the force that's exerted by all those gas molecules create a certain kind of pressure on you. And so it's not just pressure that's around you also, but it's pressure that's above you. And so the deeper you are in the atmosphere, basically close to the surface of the Earth, you're going to have more air pressure. So a couple of links between temperature, density, and air pressure. Density basically means the particles are closer together. And as you can see in this, we'll say vertical profile of air pressure, higher density means higher pressure. So as you get farther up into the atmosphere, we have a lot less air pressure, because one of the reasons is because the molecules are very thin, spread out in the upper part of our atmosphere. Temperature and pressure are linked if the volume remains the same. So if we have, let's say, a container, or even let's say a bottle of air, and you warm that air up, then you would have increasing pressure. But in the case for this chapter, we're going to really just focus on air pressure and density. So here's another way of looking at it. Pressure is force divided by area. And that force is really gravity that's pulling most of these air molecules down close to the surface of the Earth. In fact, if you're at sea level, then it's about 15 pounds per square inch. That's a lot of weight. Now that unit is not commonly used in geography or meteorology. So what we have is something called a millibar. So that's 1,013 millibars at sea level. So keep that in mind, that one number, 1,013 millibars. So this is just another look at the vertical part of the atmosphere when it comes to pressure. And the point really here is that the air pressure decreases very dramatically within the troposphere. So in an area around here where you might see airplanes fly, the air pressure is much lower than it is at the surface right here. But then that decrease in air pressure kind of flattens out as you get farther up into the upper parts of our atmosphere. So back down to the surface, what kind of air pressure readings do we usually have? Well, if we have an extreme low pressure system, we might see values down to 980. If we have a strong high pressure system, we might see values up to 1050. This here is a normal range. Now in California, we barely see this range. We're much closer to, let's say, between 1,000 and 1030. Around the world, though, hurricanes are known to have the lowest air pressure readings. The record low pressure is 870. That's at the surface of the Earth. That's quite low. The highest air pressure reading on the surface was 1084. And that was in Siberia due to extremely cold weather. In this case, the cold weather actually created such an area with such high density that it created also a very high or very strong high pressure. So what does that have to do with wind? What causes wind? So you see some dramatic examples of wind, and wind all over the world has done quite a bit of damage to certain structures, to communities, whether we're talking about hurricanes, tornadoes, or even in California with Santa Ana winds. So maybe you don't really know what causes the wind. One of the most important force that is behind all wind is the pressure gradient force. And mathematically, the pressure gradient force, well, we're going to skip this part for now, but if you want to know what the mathematical treatment is for pressure gradient force, it's really just a change in pressure. Let's keep it simple. It's a change in pressure over a horizontal distance. It's that simple. So we can look at it this way. So we have air molecules on the left-hand side, and there's a lot of air molecules on the left versus what's on the right. So nature doesn't like imbalance, so what's going to happen is you're going to have these molecules moving from left to right. And the movement of air molecules is wind. On a map, we draw lines of equal air pressure. And those lines are called isobars. So over here on the left, it's showing a pressure reading of 1020, but on the right, 1018. So air wants to move directly from that high to the low. And by the way, with this force, air is moving perpendicular to the isobars. On a real-world map, you may not see air moving directly across isobars because there are other forces involved. But generally speaking, air wants to leave high-pressure systems and move into low-pressure systems. Another way of looking at it is looking at it from the side. Air down here leaving the high and going toward the low. And this is just showing you, this diagram right here is showing you another way of looking at it through isobars. Again, with the pressure gradient force, air goes from the high to the low, and there's a right angle here between the isobar and the force, which is also in this case the wind. Now, when we get wind, that moves across the Earth long distances. Because the Earth is rotating, we get something called the Coriolis force. Coriolis force is kind of hard to explain. That's why I've posted some videos on Canvas to help you understand the Coriolis force a little bit better. Essentially, the Coriolis force is there because the Earth rotates. Let's look at an example here. We have an airplane that's moving from the North Pole, and it wants to go to South America, Quito, South America. Now, pilots are aware of the Coriolis effect. If they're not, then they will never get to their destination, especially if it's long distance. So if the pilot did not know that the Coriolis force existed, then that pilot would end up somewhere in the middle of the Pacific Ocean, because as this airplane is flying from the North Pole towards South America, the whole Earth is rotating counterclockwise. And so it makes it offset a little bit. So bottom line here, if you're in the direction that the airplane is flying, or if you're in the wind, if you are the wind, you want to veer off to the right in the northern hemisphere, but it's to the left in the southern hemisphere. Now what that does is if we're looking at the northern hemisphere, we have air that wants to go from the high to the low, but then eventually it gets curled to the right. Now the moment that this air is parallel to the isobars, then the wind actually stops changing direction. We have something called a geostrophic wind. This really only happens in our upper atmosphere, because in our upper atmosphere we have the pressure gradient force and the Coriolis force. So around centers, so we're talking about circular isobars. Around centers of highs and lows, we've set up a certain kind of flow. Air always moves around a low in the northern hemisphere counterclockwise, and it moves clockwise around a high. In the southern hemisphere, air moves clockwise around a low, but counterclockwise around a high. So you can kind of think of the Coriolis force as a twisting force. So it makes air want to move around, to curl, and it offsets from the original direction that the pressure gradient force wanted it to go. So that's in the upper atmosphere. What about at the surface? Well, at the surface, we have something called friction. And friction slows the wind down. We need friction to actually walk. Great example is if you're trying to walk over ice. But what it does with the air at the surface creates a little turbulence, and it slows the wind down. So winds higher up in the upper atmosphere, as shown as are much faster and stronger. So what that does in terms of isobars is that the Coriolis force, by the way, is not as strong if the wind is slower. So faster the wind, the greater the effect of Coriolis. What that does here is instead of the wind going parallel to isobars, so that doesn't happen, wind actually moves toward the low, but at an angle. And so the wind actually crosses isobars, but at about a 45-degree angle if you're dealing with rough surfaces like mountains, and maybe around 30 degrees if you're dealing with flat terrain. And around centers of highs and lows, we have air that still moves counterclockwise, but it spirals into a low. air spirals out of a high clockwise. And then in the southern hemisphere, air spirals into the low clockwise and out of a high counterclockwise. So this is an example where we add pressure gradient force, Coriolis, and friction all together to create surface winds. So as a recap, we started out with pressure gradient force alone. Air moves directly from high to low at a perpendicular angle. With the upper atmosphere, technically the upper troposphere, we have wind parallel to isobars, and we call those geostrophic winds. So, for example, the jet stream, if you're looking at jet stream in relation to isobars, then the jet stream would move parallel to isobars. But once we get back down to the surface of the Earth, then we have air that spirals and they cross the isobars at about, let's say, anywhere between a 30 to a 45 degree angle. Now keep in mind that the Coriolis force won't really be a factor with short distance winds or really slow winds. So when we deal with the Coriolis force, we have to deal with winds that move over, let's say, more than 1,000 miles or so. Large scale winds. Okay, so what we want to do now is, since we went ahead and talked about the three main forces, let's talk a little bit about patterns of air pressure across the Earth. And then we're going to get into how the Earth has set up this global circulation. So in January, it is winter in the northern hemisphere and summer in the southern hemisphere. And what we notice is some of the highest pressure readings are actually over some of the coldest areas. So temperature is one way that we can set up strong high pressures and strong low pressures. It's not the only way, but it is one way. And in this case, I just want to point out the Siberian high, which is quite cold. Now in the wintertime up north here, we have dynamic lows, air that sets up and becomes low pressure because there is movement of air, not because it's hot or cold. And these dynamic lows are responsible for some of the rain systems that we have here in California, especially the Aleutian low up here near Alaska. So we're going to stick with the northern hemisphere. Now look what we go to July. Now July, we have cooler temperatures over the water than we have over the land. This low pressure here over land is responsible for the Indian monsoon. This high pressure center here, west of us, west of California, helps inhibit any kind of rainfall that we could possibly get in Southern California, at least large scale rain systems, where we can get rain systems in the winter time because this high pressure system isn't really there. Now that high pressure system is there for a couple of reasons. The water here is cooler than the land nearby. That's one way. And because of dynamic factors that we'll talk about in a second here. All right, so in order to understand the global circulation of the atmosphere, we're going to start really small here. We're going to assume, okay, that the Earth does not rotate. There's no land on the Earth, and we don't have seasons. So there's very strong heating at the equator, very little heating at the poles. So what air wants to do is it wants to rise up and diverge away from the equator aloft. That sets up a low pressure system. There's less air above the equator. Now, on the flip side, air wants to converge at the poles and sink. That sets up a high pressure. So then air at the surface goes from high to low. That's very basic way of looking at the global circulation. We have one vertical circulation in each hemisphere. And that's basically what I've listed here in the slides. We have a thermal low, a thermal high. Then we have ascending air over the equator, descending air over the poles. And then at the surface, winds blow from the equator to, winds blow equatorward at the surface, poleward aloft. Now at this point, what we're going to do is we're going to make it a little bit more complex. We're going to add the Coriolis effect, and we're adding land. We still have air that wants to rise over the equator and diverge, but instead of making it all the way to the pole, the air tends to sink around 30 degrees north and 30 degrees south. What's interesting is that the sinking air does not allow rain to form because we need rising air for rain to form. So in or around 30 degrees, we have much of our deserts around the world. On the flip side, around the equator, we have air that converges and rises up. And we have a lot of our rainforests right around the equator. In fact, that ITCZ, Intertropical Convergence Zone, is a belt of thunderstorms that hugs the equator. Now those are vertical circulations. Now what happens is we set up high pressure systems along 30 degrees like the subtropical high, and air wants to move from a high to a low. So air goes from the subtropical high down to the equator. We call those the northeasterly trade winds. And we have the southeasterly trade winds in the southern hemisphere. And then after that, we have the westerlies north of the subtropical high, the westerlies. Now this steers most of our weather that we have in the northern hemisphere. Now those are just some of the pieces, but one of the most important vertical circulations that we have here is called the Hadley cell. Starts at the equator and it goes down to 30 degrees north and 30 degrees south. Another way of looking at this, kind of like this diagram as well, because it shows the vertical circulation. So we have the westerlies that spiral clockwise out of the subtropical highs and steers most of our weather that we have here in North America from west to east. We have the northeast trade winds, which blow from the high to the equator, or the southeasterly trade winds still from the high in the southern hemisphere to the equator. We have that ITCZ, Intertropical Convergence Zone. And we have our Hadley cells. Now there's a video that I've posted on Canvas that actually has a professor drawing each piece of this, and I strongly suggest watching that video to get an even better example or a better understanding of the global circulation. I do want to point out there are other vertical circulations. We have the Ferrel cell that goes from the high around 30 degrees to another set of lows around 60 degrees. And then we have the polar cell, which hugs the North Pole and the South Pole. That's not drawn very well on this diagram, but it is drawn very well on that video I've posted. Okay, so just take a step back. Jet streams, not well represented on the global circulation, but they're very important because they are fast-moving, quickly moving rivers of air at the very top of our troposphere. And they help steer much of our weather, just like the westerlies. They help steer much of our weather in North America from west to east. And we have two kinds. We have the subtropical jet stream, which is focused in the southern part of our country, and it's not as strong. But the polar jet stream is much stronger, and this is, especially in the wintertime, that drives much of our rain from the Pacific Ocean into California, and then out of California across toward the east coast. Now, jet streams can be they can be extremely fast. We're talking maybe up to 200 miles per hour. These jet streams are responsible for much of our weather systems that get very strong across east of the Rocky Mountains, we should say. And also, they help steer aircraft. So if you've ever noticed that airplanes, if you fly, let's say, from LA to New York, in the wintertime, it takes a little bit less time to get to New York than the other way around from New York to LA. The jet stream helps move airplanes even faster. And by the way, this is one of the best examples of a geostrophic wind. Now down at the surface, another kind of wind that I like to talk about is the sea breeze. And we're going to ignore Coriolis because this sea breeze is very small. It's not big enough to be affected noticeably by the Coriolis effect. But we're going to look at pressure gradient force and specific heat. So during the day, and this happens a lot at summer time, we have high pressure, I should say, let's start with temperature. We have warmer temperatures over the land than we do over the water. So air will want to rise up, and that helps create a thermal low. But over the water, air sinks, and that helps create a thermal high. So we have high over the water, low over the land. Pressure gradient force says air must go from high to low. So therefore, if you're standing on the beach, you will have a sea breeze, air that goes from the sea toward the land. Sometimes we can get a land breeze at night because the land will cool off more than the water, so we have a return flow, a land breeze. So down here we have a high over the land and a low over the water. In California, we don't get that very often, but every once in a while we do.